In lecture 38 of our series on numerical methods and civil engineering, we are going to talk about integral equations, and basically I will give a brief introduction to integral equations for those who are not familiar with them, and then we will talk about numerical techniques for solving integral equations. In the last two lectures, we saw that linearly independent basis functions can be used for solving partial differential equations. In fact, as we will see in this lecture, linearly independent basis functions have a wide variety of uses. They can be even used for solving integral equations. Now, what basically are integral equations? Well, an integral equation is as the name suggests, is an equation where the unknown variable, the variable we are trying to solve for, is under in an equation with under an integral sign. So basically an integral equation is an equation in which the unknown function appears under an integral sign. If in addition, so that is basically the most fundamental definition of an integral equation, an equation like the equation you see at the bottom of this slide, where the unknown function here being y, it is inside this integral. It is inside this integral. As you can see, there is this y of xi. So the unknown function appears within an integral. Remember, what is a differential equation? In a differential equation, the unknown function typically appears within a derivative, right? It involves the derivative of the unknown function. An integral equation, on the other hand, it involves the integral of the unknown function. So that is the most fundamental definition of an integral equation. And remember, what is a linear differential equation? In a linear differential equation, the coefficients of that differential equation, they are independent of the unknown variable. They do not depend upon the unknown variable. For instance, c dx dy dx plus b d2y dx square, c and b do not show any dependence on y. They are independent of y. That is why it is a linear differential equation. For instance, here, if in addition the equation only involves linear functions of the unknown function, it is a linear integral equation. For instance, if this f does not show any dependence on y, or this alpha, for instance, the best way to look at it is this coefficient alpha. This coefficient alpha shows no dependence on y, that is why it is a linear differential equation. So there are two main types of integral equations. They are known as, the first type is known as the Fredholm equation, and then there is something known as the Volterra equation. The Fredholm equation always has this form, right? It involves the unknown function, some coefficient times the unknown function, plus you can think of this as since we are civil engineers, one can think of this term as an excitation or a load term, and in addition there is this unknown function sitting inside the integral, right? So this is a Fredholm equation, and you can see the bounds, the limits of this integral are a and b, and a and b have no dependence on either x or y, right? A and b are just constants, right? So the limits of the integral are constants. That is a Fredholm equation, and that is a fundamental difference between a Fredholm equation and a Volterra equation, as we will see later on. So here yx is the unknown function, while kxi, this k is a very important thing, and we will see that it is the properties of this k, the eigenfunctions of this k, these are very, the properties of the k determine what are the eigenfunctions. I shouldn't go too far ahead of myself, but what I am trying to say is that the properties of this k determine many things about the integral equation, how we can solve the integral equation, what are the possible solutions, and things like that. So this k is known as the kernel of the integral equation. It is the kernel of the integral equation. So in addition, there are alpha x and fx, which are known functions. So all k, alpha and f are known functions, while y is the unknown function, and we are trying to solve for y, right? We are trying to solve for y. So, in this equation the unknown function is y, alpha, f and k are known functions. Alpha is a function of x, f is a function of x, k is a function of x and an intermediate variable xi, right. And in addition there are constants. The constants are lambda, a and b. These are also known constants, right. And while it is not essential in practice, the functions in practice, when I say in practice, I mean that in physical problems, right, because we are trying to use numerical methods to solve physical problems. So, we are trying to set up models for physical problems. In case of physical problems, it turns out that these functions k, x, xi, alpha, x and fx are continuous in the interval a and b, right. So, we will during the course of this lecture, we will confine ourselves to situations where k, x, xi, alpha, x and fx are continuous in the interval a to b, which is the interval of interest. I mean, it is not essential, but it is not practical. That is why we will confine ourselves to that. The function k, x, xi, which depends, you can see, depends on the independent variable x as well as an auxiliary variable xi, and as I mentioned earlier, it is known as the kernel of the integral equation. And you can see that if we know the kernel, right, and if we know how to evaluate this integral, how to solve the problem, right, for a certain kernel, right. Suppose I have a certain kernel and I know how to solve the problem, how to solve the integral equation for a certain problem, then whatever be the value of f of x, it is very easy to solve, right. Similarly, as you know, in case of differential equations, the differential equation, the solution of a linear differential equation has got two parts, right. It has got the homogeneous solution and the particular solution. The homogeneous solution does not change, right, with the loading, with whatever be your excitation, whatever be your load, the homogeneous part does not change. It is only the particular solution that changes. So, similarly, we will see in case of integral equations that if we can solve the homogeneous integral equation. What is the homogeneous integral equation? It basically involves an integral equation where this f x is equal to 0, right, where this term is equal to 0. If we can solve the homogeneous integral equation, then solving the effect, including the effect of the forcing function, including the effect of the term f of x, is like incorporating the effect of the particular solution, incorporating the effect of the load. But the homogeneous part, the part which is independent of f of x, remains the same. So, as I said, if the upper limit of the integral in case of a Fredholm equation, we saw that it was a constant, but in case it is not a constant, if there is for instance here, you can see the upper limit is x, small x, right, it is our independent variable, right. Since the upper limit is x, then it is, rather than the constant b, the integral equation is known as Volterra's equation, right, it is known as Volterra's equation. So, that is the most important difference between a Fredholm equation and a Volterra equation. The form are the same, right, except that in the Fredholm equation the integration limits are constants, while in case of the Volterra equation the upper bound is the variable x, right, the upper bound is the variable x. Now, one can ask that why do we have to incorporate the effect of this lambda separately? We could as well have put it inside the kernel, right, and made defined as suppose k prime or k star and included the effect of lambda within the kernel. But why don't we do that? Because there are reasons why including that parameter lambda separately is useful, and we will see what are those reasons as we go further in the lecture. The constant lambda can be incorporated in the kernel k x xi. However, in many problems it arises naturally. It turns out that when we model a physical problem using integral equations, there is a physical quantity like lambda, right, which has a physical meaning, right. So it makes sense to separate it out, because it might be the value of lambda might be measurable from experimental data, right. So it is important to separate it out. In addition, mathematically it has got, we will see later on, it has got a certain implication as well, right. So the main reason why we do not include it in kxi is because in many problems it has a physical meaning, and number two, it has a in purely mathematical terms we will see that it has a special mathematical meaning as well, right. So it is clear from either if we look at the Volterra equation or if we look at the Fredholm equation, that if the function alpha x, the coefficient of the function y of x on the left hand side is 0, then what is going to happen? Then we have an unknown function, we have an integral equation where the unknown function appears only within the integral sign, right. It appears only within the integral sign, it does not appear outside the integral sign. So in that case we call these sort of integral equations of the first kind, right. These Fredholm or Volterra equations where alpha is equal to 0 are known as integral equations of the first kind. If alpha x is not equal to 0, it is always possible to convert, as we will see. So we have this alpha x, right. By doing suitable manipulations, it is possible to make this coefficient of y of x 1, right. So we will see how that is done. So if we divide throughout by root of alpha x, what do we have? So we had alpha x, I am dividing throughout by root of alpha x. So I have root of alpha x yx is equal to fx by root of alpha x plus lambda, I am considering a Fredholm equation now. So lambda integral within a to b k of xi divided by root of alpha x. So that was the root of alpha x I am dividing, and then I multiply the top and bottom with root of alpha xi, right. And now you can see it is quite possible to get rid of my alphas from the left hand side altogether, because now if I define another function y prime of x which is equal to root of alpha x yx, then I will have y prime of x is equal to f prime of x plus lambda integral a to b k prime of xi y prime of xi, right. So again we again recover a Fredholm equation, but now the Fredholm equation on the left hand side, y, the unknown function, has a coefficient of 1, right. It has a coefficient of 1. So by suitable manipulation and change of variables, the integral equation can be written in the form such that alpha is equal to 1. So if we denote root of alpha x yx is equal to y prime x, this if we denote as k prime of xi, we get y prime of x is equal to f prime of x plus this, which is exactly a Fredholm equation with alpha is equal to 1, right. So this is a Fredholm equation of the second kind, and if it is always possible to convert a Fredholm equation of the second kind where the alpha is not 1 to a Fredholm equation of the second kind where alpha is equal to 1 by doing this sort of change of variables, right. By doing this sort of a similar operation can be performed for Volterra equations, and integral equations with alpha is equal to 1 are known as integral equations of the second kind. And and one thing nice about this transformation is that suppose my kernel K was symmetric. What do I mean when I say that the kernel is symmetric? It is symmetric in its arguments, right. So it is symmetric in x z, right. So it will involve terms like x z, x square z square, x cube z cube, right, x4 z4. It is symmetric in x z, right. So if it is if my kernel was symmetric in x z, by performing this operation I am going to preserve the symmetry of the kernel, right, because you can see I am dividing by root of alpha x root of alpha z. So I am preserving symmetry. It is symmetric, it is still symmetric in x z, right. So, in case the original kernel kxz is symmetric, k prime xz, which I define like this, is going to be symmetric as well, right. Now, the symmetry, so recall when we were looking at many classes back, when we were looking at linear systems and we were considering the properties of a linear system, we looked at the properties of the coefficient matrix, right. And we said that when the coefficient matrix is symmetric, very nice properties follow. Why? What are the nice things about it? Well, if it's symmetric, it turns out that all its eigenvectors are orthogonal, right. For a symmetric matrix, the eigenvectors are orthogonal to each other, right. So, similarly, for a symmetric kernel for an integral equation, the eigenfunctions of that integral equation become orthogonal. If an integral equation has a symmetric kernel, the eigenfunctions of that integral equation are going to be orthogonal, right. So that is the most important benefit of having a symmetric kernel. Now, so we have looked at integral equations where there is one independent variable x, right. There was only one independent variable x. Look at those equations. There was only one independent variable x. The variable xi is just an intermediate variable because it gets integrated out. You can see that after you evaluate this integral, xi vanishes, right. So, there is just one independent variable x and the dependent unknown function y, right. In case there is more than one independent variable, it is also possible to have integral equations with more than one independent variable. For instance, if we have a two-dimensional Fredholm equation, then it is of this form. You can see in addition to x, there is another independent variable y, right. In addition to x, there is another independent variable y. So, here which is the unknown function? Obviously w, right. W, which is a function of x and y, is what we have to try to find, right. We have our physical problem gave rise to this equation. We model our model for the physical problem gives rise to this integral equation, and by solving this integral equation, we will find our unknown function w, right. We will find our unknown function w. A fundamental difference between an integral equation and a differential equation is how an integral equation incorporates boundary conditions. Well, you know that if you have a differential equation, if you are solving any differential equation, for instance a differential equation commonly encountered in civil engineering, for instance the vibration of a rod, right, or the vibration of a string, right. So, in all those differential equations, you know that you have to specify the boundary conditions, right. So, in addition to having the differential equation, you need the boundary conditions. So, unless you specify the boundary conditions in addition to the differential equations, the problem is not well posed. You cannot find a solution to that problem. However, it is quite different in case of integral equations, because the integral equations in this are actually self-sufficient in the sense that they do not need to specify boundary conditions separately for integral equations. They include the boundary conditions are included as part of the integral equation itself. It is part of the formulation of the integral equation itself. You do not need separate boundary conditions. So, integral equations are different from differential equations because initial and boundary conditions do not have to be specified separately. So, the integral equation contains a complete formulation of the problem, including initial and boundary conditions. And we will see how that happens by looking at some examples. And before we do that, I want to establish some sort of equivalence. So, typically in most cases, if you have a differential equation which describes a physical phenomena, it is possible to have a corresponding integral equation describing that physical phenomena as well. Only thing is that the integral equation not only incorporates the information that is carried by the differential equation, it incorporates the boundary and initial conditions as well, right? So for many integral equations, an equivalence with the corresponding differential equation and initial and boundary conditions can be established relatively easily. But in order to do that, we have to look at a little bit of formalism, right? In particular, we have to look at this result, right? Unless we understand how we have this result, it is not possible to establish the equivalence. So this is the result, which says that if I have a function f, which is a function of a single independent variable, right? And if I integrate it n times, if I integrate the first time, f is a function, I treat f as a function of x1, right? And I integrate it within the limits a to x2, right? So then if I integrate fx1 within the limits a to x2, what am I going to get? I am going to get a function of x2, right? I am going to get a function of x2. And then I integrate that function of x2 again within the limits a and x3. So I am going to get a function of x3, and similarly if I continue to integrate this n times, I get a certain function which is going to be my final integration limit is x. So finally I end up with a function of x, right? So this function of a single variable, I am integrating it n times with variable limits, right, with my variable limits, and I end up with a certain function. And if I do this, it can be shown that doing this integration n times, instead of this, if I performed this integration, I would get the same result. If I took my function f, I multiplied it by x minus xi to the power n minus 1, integrated it with respect to xi within the limits a to x. Remember, my final limits are a to x on the left hand side as well. So if I do that, that is equivalent to integrating it n times, right? This is a very important result, and we will use this result in showing the equivalence between differential and integral equations. How can we prove this? Well, it can be done in the following manner. To do that, I define this function in of x, which is basically the right hand side of this equation. I call in of x where n is greater than or equal to 1 and a is a constant. A is a constant, x is most definitely not a constant, right? So if I define it like this, and then if I take the derivative with respect to x, what do I get? If I take din dx, I am going to get n minus 1 x minus xi n minus 2, right? f xi d xi, and in addition I will have this term. Why will I have this term? Because my integral has a variable limit, has a variable upper limit. So if you recall from your integral calculus, that if I take the derivative of an integral and the integral has limits, has bounds which are not constant, I have additional contributions, and in this case this is going to be dx, right? It will involve the derivative of the limit and times the function evaluated at this limit, minus if this limit were also not a constant, I would have to evaluate the derivative here, right? I would need to take the derivative of this times the function evaluated at this point, right? So in this case only the upper bound is non-constant. So this is going to give me, if I take the derivative of x, that is going to give me 1, right? And then I will have to evaluate this function at that value. So x minus xi n minus 1 f xi, I will have to evaluate it at xi is equal to x, the derivative of x giving me 1, right? And this is the part where I just brought the derivative inside the integral, and that gave me this contribution. So I have these two terms, and if n is greater than 1, you can see what's going to happen. Well, at xi is equal to x, this term is going to go to 0, right? This term is going to go to 0, and I will be left with n minus 1 a integral a to x x minus xi n minus 2 f xi d xi. And if you look at it closely, this is nothing but the n minus 1 times, if you look at that term, what is that term? That term is equal to I n minus 1, because we defined our I n to be this, right, x minus xi to the power n minus 1. So I n minus 1 is integral a to x minus xi to the power n minus 2 f xi d xi. So this term is going to be n minus 1 I n minus 1, right. So this is what we get, and in case if n is, so this was when n was greater than 1. If n is equal to 1, what's going to happen? In that case, n is equal to 1, so this term becomes 1. So this term goes to 0, 0 to the power anything is equal to 1. So and then we have f of x. So this term is going to be f of x, right. This term is equal to going to be f of x, and that term is going to contribute 0 because n is equal to 1. So this term becomes 0, right. So if n is equal to 1, we get di1x dx is equal to f of x. And taking repeated derivatives in this manner, you can look at this. So if I take repeated derivatives of in of x, what am I going to do? If I got the first derivative, if I took the first derivative, I had n minus 1. If I take repeated derivatives like that, k derivatives in fact here I have shown, right, then I get n minus 1, n minus 2 through n minus k I n minus k x, right, if n greater than k, right. So this is what we get by taking repeated derivatives. And if k is equal to n minus 1, if k is equal to n minus 1, so dn minus 1 in dx n minus 1, and here what we are going to get on the right hand side is n minus 1 n minus 2 through 1 times eventually I have I1 of x, which is going to give me n minus factorial of n minus 1 I1 of x, right. So this has this nice property, this integral in has got this nice property that by taking its derivatives can be expressed in terms of a it can be expressed recursively, right. Now from from the definition of in of x, it is clear that if at x is equal to a, this thing is going to be 0 for all when n is greater than or equal to 1. As x is equal to a, the integral limits become a and a, so it is going to become 0. So since the derivatives can be expressed in terms of the lower in, so dn minus 1 in dx n minus 1 for instance can be represented by in terms of I1, and we have, as we have seen before, so dk in dxk can be represented in terms of in minus k. So that means that the derivatives, all of the derivatives at x is equal to a must also be equal to 0, right. Hence from the above, the first n minus 1 derivatives of in x also vanish when x is equal to a. Is that clear? I do not think so, because in of x has got bounds x and a, right. When x is equal to a, this thing is equal to 0, and I have seen that I can express the derivatives in terms of i's, right, in terms of i's with smaller subscripts, right, smaller subscript values, right, but these are equal to 0 at x is equal to a. So that means these derivatives must also be equal to 0 at x is equal to a. So we can see that the first n minus 1 derivatives of in x also vanish when x is equal to a. So we already saw this, I1 of x is equal to we saw this di1x dx is equal to f of x. So we can write I1 of x is equal to integral of f of x1 dx within the limits a to x, right. And we saw that di2 dx can be written in terms of this. So di2 dx, so n is equal to 2, right. So this becomes 1 and this becomes 1 as well, right. So di2 dx is equal to I1x from that. So we can write I2x is equal to integral of I1x, which means, but I1x is this, so basically it is a double integral. It is a double integral of f of x1 dx1. So first I integrate it with respect to a and x2, where x2 is an intermediate variable, an auxiliary variable, and then finally I integrate it between a and x to get I2 of x, right. So I2 of x is equal to that. So and in the general case, by doing this repeatedly, it can be shown that I1 In of x is actually equal to this. So I2 of x is equal to that, right. I2 of x is integral of f of x 2 times, right, twice, integrating it twice. Similarly, if I do that n times, I am going to get back In of x, right, In of x, which is what we wanted to prove, right, because In of x, after all, remember, is this. In of x is equal to that, and we have shown that In of x is equal to this. That means this is equal to that, right. So integrating a function repeatedly n times within variable with one limit variable, and then integrating it again with respect to that variable, and doing this repeatedly n times is equivalent to taking that function, multiplying it with this x minus I n minus 1, integrating it between its final limits and dividing it by this factorial n minus 1, right. So this is the result which we are going to use in order to show equivalence between differential equations and integral equations, but it is important to understand why it happens, because it's sort of useful. Okay, so now that we have shown this, we will use this result to show that this differential equation, and we think of this as an initial value problem, right. This differential, so we can think, if it is a little confusing, if you look at x, we normally think of x as a spatial variable in civil engineering or mechanics applications. So and we might think that this is a boundary value problem. We tend to think of this as a boundary value problem, but if we think of x as t, right, this becomes an initial value problem. It depends on time, and we have to prescribe initial conditions, right, and the initial conditions we prescribe are on y, on the unknown variable, unknown function y at a is equal to 0. So a is the starting point of my analysis. A at x is equal to a, that is my initial starting point of my analysis. At y is equal to a, y is equal to y0. At x is equal to a, y is equal to y0. At x is equal to a, y prime is equal to y prime. That's a typo, it's y prime with a subscript 0, right, y prime 0. And we will see that this differential equation, by using the result which we have just proved, it is possible to convert that differential equation and those initial conditions into an integral equation. How are we going to do this? Well, we will integrate this differential equation naturally, right. Since we are interested in integral equation and we have a differential equation, the first thing that you do is try to integrate, right. So we will integrate that differential equation within the limits a to x with integration variable x1, right, with integration variable x1. So this first term I get dy dx, the first term I get dy dx within the limits a to x, and that is equal to the integral of this cx dy dx. So I put it on the other side, so I have minus a to x cx1 y prime x1 dx1, and I have this term, so I integrate again dx1 yx1 again within the limits a to x, and finally I have this term fx which I again integrate within the limits a to x with my intermediate variable, with my integration variable x1, right. And then what am I going to do? I am going to try some integration by parts. So let's see. So dy dx, I am evaluating it within the limits x and a. So I have y prime of x, I have y prime of x minus y prime of a. So dy dx at x and at a, so y prime of x minus y prime of a is equal to minus cx1 y prime x1. So I have just rewritten it basically. This equation I have just rewritten it. So minus cx1 y prime x1 minus dx1 y x1 and plus fx1. So this is what I have, and then I will integrate by parts on this term. So I have minus cx1 y of x1 evaluated between a and x minus integral of, this is the other part from the integration by parts. So c prime of x1, I take the derivative, and y of x1. So this is the contribution, this and that are the contribution from integrating that term by parts. And then I have dx1 yx1, right. I have dx1 yx1 and integral fx1 dx1. Why don't I integrate that term by parts? Well, I don't need to, because that term only involves y, right. That term only involves y, and y is within the integral, so that seems to fit the form of my integral equation, right. Because you remember that in the integral equation I have the unknown function within an integral, I have the unknown function outside, but what I do not have are any derivatives of my unknown function y, right. So I had to integrate this term by parts, I had to integrate that term by parts, because this term involves a derivative of y, but this term does not involve any derivative of y, so I do not need to integrate it at all, right. So we get this on integrating by parts, and therefore again rearranging terms now. So I have y prime of x is equal to minus, so I am evaluating this at the limit, so I get c of x y of x plus c of a y of a. So this is just evaluating it here, and then I have this term right there, and then I have integral f of x1, and I have brought this y prime a to the right hand side, right. From the left hand side I have brought it to the right hand side. But again, so you can see that there is this surviving derivative of y prime x. I want to get rid of the derivatives, right. So I want to convert it into an integral equation, so I integrate it one more time, right. I integrate it one more time, and I integrate it again between the limits x and a. So I have yx minus ya, and then I have the integral of that term, and this term now becomes a double integral, right. Dx minus c prime x1 now becomes a double integral, and then I have a double integral in f of x as well, right. I have a double integral in f of x as well, and the integration of that term gives me ca ya plus y prime of a, but ya is equal to y0 we saw earlier, right. Ya is equal to y0, y prime a is equal to y prime of 0, y prime 0. So ca ya plus y prime a I am writing as ca y0 plus y prime 0, and since I am integrating with respect to x and I am integrating within the limits x and a, I will have this x minus a appearing here, right. So this is what I get finally, and then let's see what we can do. So now we have this appears fine, right. It is there is y, and it is lying within an integral, but here we have double integrals, right. We have double integrals a to x2 and then again from a to x. Similarly here I have a double integral between a to x2 and a to x. This is exactly of the form that we just saw a few slides ago. It is of this form, right. I have an integral instead of n integrals, I have 2 integrals there, right? So I know that I can convert it to a single integral using this relationship, right? I can convert it into a single integral using this relationship, which is what I am going to do. So this, if I use that relationship, that term gives me x minus xi d xi minus c prime xi y xi d xi. Look at this, I had dx1 minus c prime x1 y of x1 dx1 dx2, right? I can convert it into a single integral because by multiplying by x minus xi within the integral, right? I have to multiply by only x minus xi because it's a double integral. So x minus xi d xi c prime xi y xi d xi, right? That is what I get here, right? And similarly, this integral I can convert it into a single integral. So again I will have an x minus xi appearing. So I will have x minus xi f xi d xi, and of course this part remains unchanged. That part remains unchanged. Now are we in the appropriate form? It looks like we are, because look at this. So if I denote, so here are 2 integrals where y is within the integral, right? So certainly if I can add these together, and the integral limits are also the same, so if I add these two together, whatever is in front of my y, that is going to be my kernel, right? That is going to be my kernel. That is going to be my kernel because that is because I have to bring it to the standard form of the Volterra integral equation. So if I denote this thing to be k of xi, and this whole thing I denote, this is going to be, this whole thing is a function of x, right? This whole thing is a function of x because here I have x, right? And this thing, if I integrate it out, this is also going to be a function of x. So this is a function of x, and this thing, if I denote by f of x, I can write this equation in that form, right? Which is basically my homogeneous Volterra equation. It is my homogeneous Volterra equation, and it is a homogeneous Volterra equation of the second kind. It is a homogeneous Volterra equation of the second kind because there is nothing, there is no alpha is equal to 1, right? So it is clear that this is a Volterra equation of the second kind with kernel k of xi, a linear function of the independent variable x. You can see that the kernel is a linear function of x, right? X is it's a linear function of the independent variable x. So that is how we could convert a second order differential equation, second order ordinary differential equation, linear differential equation with 2 initial conditions into an integral equation, So implicit in the transformation is the assumption that the coefficients d, c, c prime as well as the function f are integrable, because you can see that we have integrated them repeatedly, right? We have integrated f, we have integrated c prime, we have integrated d, so those are integrable. So that is what we have assumed. It is similarly possible to go the other way. It is possible to transform an integral equation to a differential equation. How can we do that? Well, let us see. And this time, the first time we converted the differential equation into a Volterra integral equation. Now we will start with the Fredholm equation and see what differential equation results from that Fredholm equation, right? So again we are going to consider a Fredholm equation of the second kind. But this Fredholm equation, you can see this is a Fredholm equation of the second kind, that is true, but the kernel is the kernel function is different in different intervals, right? So when x is greater than xi, this kernel is given by this function, say, and when x is less than xi, the kernel is given by that function. Is the kernel continuous? Well, you can see, if you look at it closely, you will see that when x is equal to xi, the kernel is actually continuous, right? But so this is a Fredholm equation with a kernel, and the kernel has got two representations in two different intervals, which is not a problem, right? Because this is an integral, and so that function, it is a certain function in a certain region, and then it's a different function in a different region, right? That is always possible, and it is also continuous, right? There is no discontinuity at x is equal to xi, which is perfectly fine. So we rewrite this equation in this form. So basically I am breaking it up into two. So my original integral limits were between 0 and L. So I am going to break it up into two regions, between 0 to x and x to L, right? And since my integration variable is xi, when I integrate between 0 to x, xi is always less than x, right? Xi is always less than x, and when I integrate between x to L, xi is always greater than x. So in this region, which my xi is always less than x, so my kernel is going to be this one, right? My kernel is going to be that one, while in this region xi is always greater than x, so my kernel is going to be this one, right? This is going to be my kernel. So now I have y of x in this form, where you can see that the kernel is different in these two regions. Between 0 to x it is this kernel, between x to L it is that kernel. And then we differentiate. So now when we were trying to go from differential equations to integral equations, we were integrating. Now we have to do the opposite. We have to take derivatives, right? We have to take derivatives. So differentiating both sides, I have dy dx is equal to lambda 0 to x, so minus xi L. So again you can see, in order to take the derivative of this thing, it is not, I have to account for the fact that the limits are not constants, right? The limits are not constant. So first term will be just the plain derivative, right? So derivative of xi by L, L minus x, so that is going to give me minus xi by L, y xi d xi, then plus I have the derivative of x, right, dx, so that is going to give me 1, and then I have to evaluate this function at x, so that is going to give me x by L, L minus x, y of x, right? I do not have to account for this part, this in this lower limit, because the lower limit is constant, right? And then I have this thing, I have that thing, which is going to give me which is going to give me this term, right? This term. So again, if I take the derivative, bring the derivative inside, I have L minus xi by L y xi, right? And now in this case the lower limit is a non-constant, so I have minus sign, right? Minus derivative of this, which again gives me 1, derivative with respect to it gives me 1, x, which gives me 1, and then I evaluate this function at xi is equal to x. So I evaluate this function at xi is equal to x, which gives me x by L, L minus x, y of x, right? So this is what I get, and then you can see that these two terms cancel each other. So I am left with something like that, which is basically I have brought these two integrals together, right? I have added them, and then I take the derivative of this again. I am left with lambda by L. So again now you can see, if I take the derivative of this inside, there is no dependence on x, right? So inside it gives me 0, right? So the only part which is going to give me a contribution is because of the non-constant limit. So derivative of that is going to give me 1, and then I have evaluate this at xi is equal to x, so minus xy of x minus, again this term is independent of x, so derivative of that is going to give me 0, and then but the lower bound is still dependent on x, so again I take the derivative of that times the function evaluated at xi is equal to x, so that gives me L minus x y of x, and that gives me minus lambda y of x. So you can see that finally we have arrived at a second order differential equation from our initial integral equation. From our initial integral equation we have arrived at a second order differential equation like this. And this yields the equivalent differential equation. And the boundary conditions, what are the boundary conditions? We can get the boundary conditions by setting x is equal to 0 and x is equal to L in star. Remember that our integral equation, for the integral equation we did not have to specify any boundary conditions. But how do we get the boundary condition? But for the differential equation I do need boundary conditions. So how do I do that? I set x is equal to 0 and x is equal to L in this, right. When x is equal to 0, what do I have? When x is equal to 0, that means that the kernel is of this form, right, because my integration limits are between 0 to L, and xi must be, with x is equal to 0, then xi has to be greater than x, because xi goes from 0 to L, right. So when x is equal to 0, xi must be, so this is my kernel, and look at what the kernel will become when x is equal to 0, it is going to become 0, right. So then I have 0 inside the integral, so that means at y of 0 this is going to be 0. Similarly when x is equal to L, this is going to govern, right, x is equal to L, this is because x is always going to be greater than xi. So in that case what does the kernel become? The kernel again becomes, if I put x is equal to L here, the kernel also again becomes 0. So again, so at y is equal to L, this thing again becomes 0, and then I recover my boundary conditions for my differential equation. The boundary conditions can be obtained by setting x is equal to 0 and x is equal to L in my integral equation, taking care that I choose the appropriate branch of the kernel appropriate to x is equal to 0 or appropriate to x is equal to L, and once I do that I recover the boundary conditions. Now, as I mentioned, the kernel in this example has two branches, right. It has a different analytical representation when x is less than xi and x is greater than xi. However, as I also mentioned, if you look at it, it is continuous at x is equal to xi, so no problems at all, right. However, there is a discontinuity in the slope, obviously, right. So it is represented by a certain function in a certain range, and in the adjacent range it is represented by a different function. In this case it has a discontinuity in the slope. If we evaluate del k del x, this is equal to 1 minus xi of L for x less than xi, dk dx is equal to minus xi of L for x is xi, and you can see that there is a jump in the derivative, and the jump is equal to minus 1 as x increases. So at x is equal to xi there is a jump, right, there is a jump in the derivative. Also, since del chi, as you can see in both these ranges, dk dx is independent of x, right, there is no dependence on x, so that means that the second derivative of the kernel is 0, right, is independent of x throughout the time. If I take the second derivative of the kernel with respect to x, that is going to be 0 throughout the interval. Again, from the expression for kxi, it is clear that kxi vanishes at the endpoints of the intervals at x is equal to 0 and x is equal to L, which we just saw a while back, right? So it is x is equal to 0, x is equal to L, it is 0. So the kernel satisfies the homogeneous form of the differential equation, right? So this was my differential equation. The kernel satisfies this differential equation, but with a 0 on the right hand side. It satisfies the homogeneous form of the differential equation. In addition, it satisfies the boundary conditions homogeneously, and in addition it has this very, very important property that it is symmetric in x and xi. And we will talk about the properties of symmetric kernels in the next class. Thank you.